Hi everyone, this is NLP Corgi. Today's deep dive is about the paper from Moonshot AI, Kimi K2.5, Visual Agentic Intelligence. Kimi K2.5 is Moonshot AI's new open-source model aimed squarely at what they call general agentic intelligence. It doesn't just read and write text. It sees images and videos, reasons about them, calls tools, and coordinates multi-step tasks. On top of that, it introduces a new orchestration framework called Agent Swarm, which lets many specialized agents work in parallel instead of one model doing everything sequentially. Recent frontier models already show strong agent-like behavior. They can plan, call tools, and reason over long chains of steps. But real-world tasks rarely live in text alone. They involve screenshots, PDFs, videos, codebases, and web tools. If you try to handle all of that with a single agent stepping through actions one by one, latency explodes and you quickly hit a ceiling on task complexity. Kimi K2.5 is designed to break through those limits by unifying text and vision and by moving from a single agent to coordinated swarms of agents. This figure gives a bird's-eye view of Kimi K2.5. It shows how the model stacks up against leading proprietary and open-source systems across reasoning, coding, vision, and agentic benchmarks. The key message is that K2.5 is not just competitive in one niche. It delivers strong, often state-of-the-art performance across a wide spectrum of tasks, from math and science exams to long video understanding and complex web search agents. The design of Kimi K2.5 rests on four big ideas. First, it's natively multimodal. Text and vision are trained together from early on, not bolted together at the end. Second, they use what they call zero-vision supervised fine-tuning, where they only fine-tune on text but still manage to activate visual reasoning and tool use. Third, they run reinforcement learning jointly on text and vision tasks, and find that visual RL actually improves pure text benchmarks. Finally, they introduce Agent Swarm, a framework where a trainable orchestrator learns when and how to spin up specialized subagents and run them in parallel. Kimi K2.5 starts from the Kimi K2 base model, which is a trillion-parameter mixture of experts transformer, with about 32 billion parameters active per token. On top of that, they add a shared 3D vision encoder that handles both images and videos in a unified way. The model is then jointly pre-trained on roughly 15 trillion tokens that mix text and visual data. Later stages extend the context window up to 256,000 tokens, so it can handle long documents and thousands of video frames in a single pass. A central design question is how to mix vision tokens with text during pre-training, given a fixed total token budget. Many prior systems add vision late and at high ratios, treating multimodality as an add-on. The K2.5 team systematically varied both the timing and the ratio of vision tokens. They found that, under a fixed budget, early fusion with a relatively low vision ratio consistently yields better overall performance. In other words, it's better to expose the model to both modalities from early on, instead of shocking a mature language model with a flood of images at the end. Table 1 and the associated learning curves show how different training strategies behave when you keep the total number of text and vision tokens fixed. When vision is injected only in the middle or late stages, text performance dips sharply when images first appear, then slowly recovers. Early fusion with a lower vision ratio avoids this disruption. It yields better final scores on both visual tasks like grounding and OCR, and on text tasks like knowledge and reasoning. This is what the authors call native multimodal pre-training. For vision, Kimi K2.5 uses a single encoder called MoonVit 3D. It's designed to handle images at their native resolution without chopping them into tiles, using a Navi-T-style patch packing scheme. To extend this to video, it groups up to 4 consecutive frames into a spatiotemporal volume, flattens the patches, and runs the same attention mechanism across both space and time. A lightweight temporal pooling step then compresses each group of frames by a factor of 4. This lets the model process videos that are roughly 4 times longer within the same context window, while sharing all weights between image and video processing. After pre-training, the team does supervised fine-tuning, but with a twist. They don't show the model any images at this stage. Instead, they use text-only data, where image manipulations are represented as code snippets, executed in an IPython environment. For example, counting objects or measuring areas is done via image processing code, not by directly labeling images. Surprisingly, this zero-vision SFT is enough to activate visual reasoning and tool use, thanks to the strong alignment learned during joint pre-training. In contrast, when they tried adding small human-designed visual SFT datasets, performance on visual agentic tasks actually got worse. likely due to low data quality and narrow coverage. Zero Vision SFT gets the model to pay attention to images, but it's not yet robust. To refine visual behavior, the authors run outcome-based reinforcement learning on tasks where you must use vision to succeed. These include object grounding and counting, chart and document understanding, and vision-heavy STEM problems. The reward is based on whether the final answer is correct, not on hand-labeled intermediate steps. Starting from the Zero Vision SFT checkpoint, they scale up the amount of visual RL compute and see smooth monotonic gains on benchmarks like MMMU Pro, Math Vision, Char XIV, and OCR Bench. A natural concern is that optimizing for vision might hurt pure language performance. To test this, the team evaluated several text-only benchmarks before and after visual RL. The results are striking. MMLU Pro improves by 1.7 points, GPQA Diamond by 2.1, and Longbench V2 by 2.2. The authors argue that visual RL improves the model's calibration and structured information extraction, which also helps on text questions that resemble counting, OCR, or layout reasoning. In short, visual RL doesn't just avoid harming language, it actually makes it better. Building on these findings, Kimi K2.5 adopts a joint multimodal RL setup. Instead of having separate experts for text and vision, they group tasks by ability, knowledge, reasoning, coding, and agentic behavior. Each domain includes both pure text and multimodal problems, and a unified generative reward model evaluates outputs across all of them. This design encourages skills learned in one modality to transfer to the other. For example, better visual grounding can improve text-only extraction tasks, and stronger textual reasoning can help interpret complex charts and diagrams. Reasoning models often get better when you let them think longer, but that quickly becomes expensive. If you simply train under strict length limits, models tend to overfit to short chains of thought and stop benefiting from extra tokens at test time. To address this, the authors propose a heuristic called toggle. Training alternates between two phases, one where the model must solve problems within a learned token budget, and another where it can use the full token limit. The budget is estimated from the lengths of successful solutions. This alternating scheme reduces average output length by about 25 to 30% across many benchmarks, while keeping accuracy nearly unchanged. Most current agent systems run as a single chain of reasoning and tool calls. As tasks get broader and deeper, this linear structure becomes a bottleneck. Agent Swarm tackles this by introducing a trainable orchestrator that can create and manage many subagents. The subagents themselves are frozen models, instantiated from earlier checkpoints. During reinforcement learning, only the orchestrator is updated. It learns when to break a task into subtasks, how many subagents to spawn, what roles they should play, and how to schedule them in parallel. Subagents are treated as part of the environment, which simplifies credit assignment and stabilizes training. To train the orchestrator, the authors propose Parallel Agent Reinforcement Learning, or PARL. The reward has three parts. First, a performance term measures whether the overall task was solved well. Second, a parallelism term rewards the orchestrator for actually instantiating subagents, which prevents it from collapsing back to a single agent strategy. Third, a finish rate term rewards subagents that complete their assigned subtasks, discouraging the orchestrator from spawning many agents that do nothing useful. Over time, the auxiliary rewards are annealed away, so the final policy focuses on solving tasks efficiently while still leveraging parallelism. In a parallel agent setting, simply counting total steps is misleading. You might spawn many subagents, but if they all run in parallel, wall clock time is closer to the length of the slowest branch. To capture this, the authors define a metric called critical steps. Each stage consists of one main agent action, plus a group of subagents that run in parallel. The duration of that stage is the main agent step, plus the maximum number of steps taken by any subagent in the group. Summing this over all stages gives the critical steps for an episode. Training and evaluation are constrained by critical steps, which pushes the orchestrator to design decompositions that actually reduce end-to-end latency, not just increase concurrency. To teach the orchestrator when parallelism is useful, the team builds a suite of synthetic and realistic tasks that are hard to solve sequentially within a fixed step budget. Some require wide search, like exploring many independent sources at once. Others require deep search, with multiple reasoning branches that only merge later. There are also tasks like large-scale file downloading and long context document analysis. Importantly, the prompts never tell the model to parallelize. Instead, the environment is structured so that parallel decomposition naturally leads to higher rewards and fewer critical steps. and the orchestrator learns these strategies through reinforcement learning. Under the hood, Kimi K2.5 uses a unified agentic RL environment that looks a lot like a modern RL framework. Environments expose a standard interface, and you can plug in toolsets, reward judges, and prompt diversification modules. The system supports both white box environments, where you control everything, and black box ones that only expose a standard LLM API. A rollout manager coordinates up to 100,000 concurrent agent tasks, including recursive subtask calls. The inference engine is co-designed with RL, exposing token-level log probabilities in a token-in, token-out API so that the training loop can correct for train-inference mismatches and stay stable. Multimodal training introduces a practical challenge. Images and videos vary a lot in size, which can overload the first pipeline stage if you co-locate the vision encoder there. Kimi K2.5 solves this with a decoupled encoder process. First, they run the vision encoder forward pass on all GPUs in a balanced way, discarding intermediate activations and keeping only the final features. Then they run the main transformer forward and backward as usual, using the same highly optimized parallel strategy as in text-only training. Finally, they recompute the vision forward and run its backward pass to update the encoder. This design keeps the pipeline balanced and achieves about 90% of the efficiency of pure text training. Putting it all together, Kimi K2.5 delivers impressive results across a wide range of benchmarks. On math and science exams like AIME 2025, HMMT, and IMO Answer Bench, it scores in the same ballpark as top proprietary models. On coding tasks, including SWE bench variants and live code bench, it is competitive with or better than leading systems. On multimodal benchmarks like MMMU Pro, Math Vista, OCR Bench, and long video suites, such as LV Bench and Long Video Bench, it reaches or approaches state-of-the-art. And on agentic search and computer use benchmarks, it often sets new highs, especially when using Agent Swarm. Table 5 zooms in on reasoning and coding benchmarks, and also reports average output length in thousands of tokens. Kimi K2.5 generally matches or improves on Kimi K2's accuracy while using noticeably fewer tokens, thanks to token-efficient RL and the toggle schedule. It remains competitive with Gemini 3 Pro and DeepSeek v3.2 on tasks like AIM, HMMT, IMO Answer Bench, Live Code Bench, and GPQA. This suggests that you can get high-quality reasoning without always paying for extremely long chains of thought. How much does Agent Swarm actually help? On BrowseComp, a deep research benchmark, Kimi K2.5 jumps from 60.6% as a single agent to 78.4% with Agent Swarm, even edging out GPT 5.2 Pro. On wide search, which stresses broad information seeking, performance rises from 72.7 to 79.0%, beating Claude Opus 4.5. On an internal Swarm benchmark designed for extreme scale tasks, the gain is 16.7 points. These results show that learned parallel orchestration doesn't just save time, it also improves the quality of the final answers. Beyond accuracy, Agent Swarm delivers large speedups. On wide search, the authors plot how long it takes to reach different target item F1 scores. As you push for higher quality, the single-agent baseline's runtime explodes, reaching more than 7 times the baseline at 70% item F1. In contrast, Agent Swarm's runtime stays in a narrow band, roughly between 0.6 and 1.6 times the baseline, even as the target score increases. That translates into 3 to 4.5 times faster completion for the same quality level, thanks to effective parallelization of subtasks. Long agentic runs often hit context limits. A common workaround is to truncate or summarize old messages, using strategies like hide tool result, summarization, or discarding all history beyond a threshold. These are reactive and can lose important structure. Agent Swarm offers a proactive alternative. It shards context across subagents. Each subagent maintains its own local history and works on a bounded subtask, while the orchestrator only receives distilled outputs. This preserves global coherence without stuffing everything into a single context. On BrowseComp, this proactive context management beats a strong discard-all baseline in both accuracy and efficiency. One of the most striking demos is a full playthrough of the game Black Myth Wukong, 24 hours of 1080p gameplay split across 32 videos, totaling about 40 gigabytes. The main agent inspects the directory, realizes the scale, and spins up dozens of subagents, each responsible for analyzing one video. These sub-agents extract frames, detect level ups and boss fights, and summarize events. The main agent then aggregates their outputs, selects key clips, and generates an interactive HTML page that visualizes the entire journey. This example shows how Agent Swarm and MoonVit 3D combine to handle truly massive multimodal workloads. Kimi K2.5 also shines on fine-grained visual reasoning tasks when paired with tools. In maze solving, it converts the maze image into a binary grid, identifies start and end points, and runs a breadth-first search to find the shortest path, then overlays the path on the image. For pie charts, it segments colors in HSV space, counts pixels per sector, and computes precise percentages, such as the combined share of green and blue. In spot the difference puzzles, it performs pixel-wise comparisons, extracts contours, and clusters them into meaningful difference regions. These examples highlight how the model can translate visual problems into code, iterate based on intermediate outputs, and arrive at exact answers. Despite its strengths, Kimi K2.5 has clear limitations. Training requires massive compute, sophisticated infrastructure, and carefully curated multimodal data, which are not trivial to reproduce. Agent Swarm introduces a new layer of complexity. You now have to train and tune an orchestrator, design rewards, and manage many concurrent agents. The benefits of parallelism also depend on the task and the tools. If external APIs are slow or tasks are inherently sequential, speed-ups will be smaller. Finally, the success of Zero Vision SFT hinges on having strong joint pre-training and high-quality text traces. It may not work as well in settings with weaker alignment or noisier data. Kimi K2.5 offers a concrete blueprint for building more general agentic systems. It shows that if you treat text and vision as first-class citizens from the start, they can reinforce each other instead of competing. It demonstrates that reinforcement learning on visual tasks can spill over and improve language-only benchmarks. And it makes a strong case that learned parallel orchestration via Agent Swarm can convert raw compute into both higher quality and faster agentic behavior. By open sourcing the post-train checkpoints, Moonshot AI is inviting the community to build on these ideas and push further towards scalable, general-purpose agentic intelligence.